Hey everybody, welcome to another session for this Shock Week. I hope you're enjoying Shock Week and realize that there's a lot of great information. If you're not aware of it, check out the YouTube channel. The entire week of the last week of May is Shock Week here on my YouTube channel, so please feel free to dive in and learn something new. I hope you enjoy this session with me and Dan Carnovale.
Yep.
I know I did.
All right. So, and that's a part of the discussion for training. So, Shock Week, we're recording this for Shock Week.
Okay.
And you're an important person because you do a lot with training. And you've created a monster here. And everybody out there, I want to introduce Dan Carnovale. I've known Dan for too long.
Since we took our PE.
Since we took our
each other, realized you knew each other. That's so long, a long time ago.
It's a long time ago. Why don't you let everybody know who you are?
Yep. So again, Dan Carnovale, I'm the director of our experience centers here in Pittsburgh and in Houston. And I've done a lot of work in the field with testing and doing things around power quality kind of things. So the thing that I kind of am very passionate about was training people on the things that I learned about. So in about 2003, 2004 timeframe, started this experience center thing and got enough momentum going to actually create what we now have here as a really kind of it's a world-class kind of training center. And to me, it's fun because Tom and I get to play with electricity. What could be better than playing with electricity and explaining to other people how it works?
Absolutely.
Feel like magic, right?
So I have my theory.
Yeah.
Here's my theory. My theory is that you graduated with a master's in electrical engineering. You went out into the field, and I know, based upon what I know about you, you did a lot of troubleshooting in facilities around power quality.
Right.
Trying to figure out, okay, why is this piece of equipment failing and all that good stuff?
Right.
And you're dealing with harmonics, transients, series resonance, all this good stuff, right?
Right.
And we can't visualize it. We can't see it. It is so hard to explain to somebody what harmonics is. And I remember the first was right behind this wall.
Yeah.
It was your first lab. And what would you took power supplies from, they were replacing all the transformers, right?
Yeah.
You took all the power supplies out and you put them in a bank. And I can remember come up here and you were like, hey, look at this. And you would turn the power supplies on and we would look at that funky waveform. And then you would turn on a filter and it would clean it up.
Yeah.
And that's just that's a visual representation of things that we know. And then all those big gray boxes we stick on the wall that you just say, yeah, this is what it does.
Well, it's funny because when you start thinking about FFTs, Fourier analysis, and all this stuff, it just becomes just a math problem when you're in school. And so to see it visually, it is super cool. And I really enjoyed it's funny you talk about those power supplies because I literally have my kids helping me wire and strip down, stuff like that, set on the back deck. So we have 360 power supplies there that represents like an office building or whatever. And it's been such a big deal, but I think people talk about stuff like that. And you learn about it, but to see it is a big thing. And then so we would use phase shifting transformers and do things like that. And I don't know, some of the most fun things though is when you see something like that, then you visualize it and you show the waveforms and then you go, wait, that's what that was. So I have all these aha moments personally. And then we just start building on that. And then we're like, oh, what if we could build a demo with this? Right. So it's funny because I had a guy in here that was PhD in electrical engineering. And I showed him one of our harmonics demos here, and he starts shaking his head. I'm like, what's wrong? He goes, what's wrong? He goes, literally, you just showed me in 5 minutes what I spent 4 years on my PhD. And I was like, wow. But the cool thing is we've evolved this stuff so much that it's become not only fun to learn, but it really reinforces the math. And that's the crazy part, right? You don't have to guess anymore. This is what it is. It's not.
Well, it's taking the theory and putting it in a visual. We can do math all day,
right?
But until you see the results of, until you actually I'm a physical learner. I have to see it.
Yeah.
I have to work on it. I do so much better, even in school. Machines lab, Dr. Black.
Yeah.
I would go in and I could set things up and I would watch it work. And then you go, that
makes sense.
makes sense. And I used to love digital the same way. I could talk about the microprocessors and how they work, but then when you lay it out on a breadboard and you turn and you press a little button and you see something happen, it's like, okay, I took the theory, I implemented the theory, and now I'm watching it. And so you look at a facility like this, where you have all the equipment on the wall, you can touch it, all of this stuff is exposed, but it's all safe. It's all
this stuff here isn't live, except for you see some of the stuff that's protected. But like in almost all of our other areas, everything up to 480 is fully energized. So behind protected barriers, but in a safe, controlled environment. So that makes it so much easier to learn rather than just, here's a PowerPoint slide of it, or here's a piece of equipment, but now you turn it on and man, it just takes it to the next level.
It does. Because you, like you say, you just, even like the power supplies.
Yeah.
It's not like you're going to, you're showing a waveform.
Right.
And then you turn the power supplies on and you watch the waveform. And then you turn a filter on, and then the waveform cleans up, and you go, "That's what that piece of equipment is doing."
It does,
and it's just phenomenal.
So for like that one in particular with all the third harmonics, everybody says, "Oh, the third harmonics add up with the neutral, and they circulate in the delta." And then you kind of, so we actually started putting meters on the input and output of transformers, and we're showing the waveforms and say, "Oh, here on the secondary you have the third harmonic and the fifth and seventh and all the odds." On the primary, you have just the fifth and seventh. So it kind of matches up with what it's supposed to be.
Right.
And then you go, well, wait a minute. Now the third is supposed to be additive from the phases. So we have 20 amps on A, B, and C. Instead of adding up to 0 like the other things do, it's 20 plus 20 plus 20. So on the neutral, we have 60.
Right.
And it's so cool when stuff like actually works out. Which is funny because when people tell us stuff that's not really true, but maybe they've heard, we're like, oh, let's just go prove it because we can show it. That's the most fun.
That is exactly right. So you've built off of this and those few examples, and I remember you had a voltage sag example as well. Watch the light bulbs drop out, and you had the high bay light,
like representing the stadium from the Super Bowl.
Yeah, exactly. And when the voltage goes down and those high bay lights go, it's going to take time to bring them back up again.
Right.
So you would demonstrate all that. Now you've grown that considerably in this facility.
Yeah.
So you had to create examples on how to take theory and what we are understand about electricity, and then implement it in a way that, okay, now we're going to demonstrate this, or you're going to experience this.
Yeah.
How do you come up with those ideas? And then where have you settled? Do you have any, can you walk us through some examples? And then we'll show some video as we go through here, but can you just walk us through, okay, we picked this and here's what we're demonstrating, here's why.
Yeah. And I'll just reinforce the hands-on part, the Eaton Experiential Learning.
Oh yeah. Okay.
So it's all about, we use kind of the tagline of seeing is believing, and people are like, what do you mean by that? Well, let me just show you. And so it started with early on with those power supplies, and we were trying to show harmonics because harmonics are probably one of the most misunderstood things because people get super excited because now you have waveforms and meters and stuff that can show that. And frankly, they've never seen it before. So they're like, oh, this is horrible. And I'm like, no, that's kind of normal. And then this is horrible. So you make the distinction. Right. So our harmonics demonstrations went from the computer power supplies to variable frequency drives. And with the drives, we can do 6 pulse drives. And then we can turn them on and we can show what it looks like on a normal system. And then we show 12 pulse or 24 pulse and show how much better it could be.
The higher the pulse, the cleaner the sine
waves. And then we could do things and that's with phase shifting on a system level. And then we could do things like you said with harmonic filters or even active filters or chokes and line reactors, because, no matter what you look at electrically, there's good, better, best, right?
Sure.
And so we always tell the young consultants that come in here, we're like, well, you could recommend the most expensive system in 6 months you won't have a job because frankly, nobody wants to buy your system.
Right.
You could recommend the cheapest one and same thing, it could fail. So when we look at, for example, anybody as a consultant or a contractor that's kind of specifying or integrating stuff into systems, we want to give them options and say, okay, here's all the different things you could do.
Mhm.
What's the best one for you? So harmonics, we go from chokes to, like I said, 6 pulse, 12 pulse, 24 pulse, 18 pulse drives. We have filters, fixed filters, switch filters. We create resonance, like you said. So if you do it the wrong way, you can make it worse, So there's lots of different things we can show in that space.
And you don't have to go all the way. You could say, correct me if I'm wrong, but you could say, look, I'm going to design a system. I'm going to not buy the most expensive over here. I'm going to go low cost over here. And over here, I'm going to want to do something that is a little bit beefier or maybe more expensive, maybe a higher pulse type of solution for different reasons.
Well, and that's why we call this a power systems experience center, right? Because it's not a component thing. So the system, like you said, okay, I'm going to apply it on the system level because I don't really care what happens down here at the low level. I know I'm going to have the stuff there. So the harmonics one has always been a big one and a fun one, frankly.
Sure.
The other one in the power quality lab that we call it, and we've done pretty much since day one, is we blow up a light.
Oh,
right?
yeah. The
So
surge.
we do the surge demo.
Yeah.
And I think like a lot of people buy surge protectors. And we just had a conversation yesterday with some of these young engineers that were here. And we said, hey, why would you put a surge protector? And they go, well, it prevents this equipment from being damaged. Okay, so that's an insurance policy. Well, yeah, I guess. And I said, do people like to buy insurance? And no, not necessarily. But if you see it work, we go, holy, that really works. So maybe I should buy that insurance. It's cheap insurance compared to the benefits. So we blow up a light bulb, then we show it with the surge protector on it. It's like a go, no go. And then we reinforce that with the waveform on a high-speed meter. And we go, look, here's the actual thing you saw at 6 million samples per second.
Yep.
It really helps to reinforce it.
Yep. Yeah, sounds so what I really, I like the demo. I like it's really cool. Watch the light bulb burning with all that good stuff, right? But what I really had an appreciation of was when you start adding conductor.
Oh, yes. Yeah.
And I tell people this. I tried to get a code requirement to limit the length of that conductor. Could not do that. We just got an informational note that said the length of that conductor and the bends
It's a big effect. Yeah.
is a big effect. But what I try to explain to people is they'll take that panel board and then they put the surge device way over there, and you go, look, I got the sale.
Yeah.
The electrician got paid to install it, but it does absolutely nothing. But when you can demonstrate that, that's when it really hits, because we can say this stuff all we want. But when you actually see it and you go, hold on, I'm really not doing anything. It's really not doing anything. It becomes a big audit.
Yeah. So what we do with that one was we show a bus connected surge protector, like a commercial one. And then we show a side mount one like 12 inches away. And then we show one 3 feet away. And just to give you the numbers, like the surge protector that we put in is rated to clamp at 400 volts. But they rate it with 6 inches of cable. So if it's bus connected, we actually can clamp at 350. And then if it's 12 inches away, it's 6 inches too far. So it's 400 plus, and it goes about 550. And then the one that's like 3 feet away literally is like almost 1500 volts. So now you exaggerate that to your point, like, oh, yeah, I put it over here on the wall 30 feet away. But you know what a lot of people tell us? They're like, well, I do that so I can see the green lights are working and I can walk by the door. And I think, well, that's great because it's not going to do anything.
Yeah, those green lights will always be there because it'll never get hurt.
Yeah. But the surge one is always fun. And so we've done that since day one. The hard part I have now is trying to find light bulbs to blow up. So
cool. So what happens when the incandescent bulbs go away? What are you going to do?
Well, they have gone away, but I bought a pallet of 5,000. So we should be okay for a couple of years. We'll be okay for a couple of years.
Until I retire.
That was my latest. Yeah. Anyway.
So he's the only guy I know that bases his retirement off of when we get out of inventory. So his boss is going to go back and check inventory.
Yeah. I think that might be a problem. We'll put that part. No. So the surge one is big. And so there's a lot around power quality. We talked about the SAG one. SAGs are the most costly thing because it affects the whole facility, and then it's funny because a lot of this stuff is, again, educational, it's say sales, but like educational things that are going to teach people what you should think of. So
when you make a decision, absolutely right.
Because okay, you could buy a UPS and put it on everything, but you're not going to put a UPS on an industrial plant. I mean, it's dirty and you have, battery issues and stuff like that, temperature things to consider. But like, since sags are so prevalent, 13 times a year, on average, people are going to lose equipment as a result of voltage sag. So we can show and demonstrate how that works and how to fix it. So it's not just showing the problem, because we can talk about problems all day, but if you can show the solution side by side, now you've got an option to
and different solutions. Like
exactly.
you said, this one will do this, so here's the limitation of it. I like the UPS demonstration that you did. You say, okay, look, we have 3 light bulbs.
Yeah.
And we're going to cause this outage, or we're going to cause you're going to shut up. Yeah. You're going to show an interruption.
Yeah.
And then the UPS takes over. One of the light bulbs blinks. The other one blinks kind of the other one doesn't change at all.
Yeah. So you have, we'll say standby UPS, which is basically a battery backup. Something bad happens. It goes, hey, something bad happens. I better switch over. That's the one that takes so long.
Yeah.
But it's about maybe 4 milliseconds. Sorry, not 4 cycles, 4 milliseconds, quarter of a cycle. And then the other one is line interactive. So it's always kind of watching and maintaining good voltage, plus or minus 1%. But then if something bad happens, it also has to switch over to the battery. So there's a little bit of a delay. And then the third one is what we'll call a full double conversion or online UPS. And then, again, do we need that for our house? Probably no. But, you think about the first one might be $50. The other one might be $200, and the third one might be $1,000 for the same electronic size. Yeah. And then try to decide which is best.
And then even the $1,000 one has those, like you pointed out, you said, look, you can have this one, but what was it? It has a challenge. It's losses. Yeah. It has losses.
It's paying for it all day, every day.
Yeah.
So in a bit, for a big data center, no big deal, right? I mean, you're expecting to do that, and it's okay.
Because the benefit exceeds.
The benefit is, but again, it's an insurance policy in that space. And then actually with the UPSs, the next demo that we did was the one with the Energy Aware, which is cool because now you've got these batteries, they're always available, but since you only need them maybe a few times a year, like the really big data centers that are using 100 megawatts of power, they go, well, I want to make some of that back. And so they're actually dumping power from the batteries back into the grid and using it like almost like a generation station. So the utility calls them up and says, hey, can you give me 50 megawatts? And sure enough, you can do it for 20 minutes or so and get rid of those peak demands. So
Yeah.
Those are the fun ones that are like new technology taking over from, you would never do that with lead acid batteries, but now that we're using lithium and other battery technologies to do it.
Oh, absolutely. Yeah, absolutely. 1 second. I just want to make sure. Yep. The one time I did this, I didn't record it. I never pressed record. No, I did a whole hour. It was like 11 to 12 at night for the next day. And I was like, oh my God. So I'm got this. I got to look for the little red line. I wish there was a better red indicator on that display. Okay. So
that's the one. So another one that actually is really popular here, which Eric Hurd put together for us out here when he was doing some stuff when he was actually going back to school and he was doing a senior design project. He goes, hey, you got a good senior design project. We did the recloser demo. So the recloser.
Oh yeah. Oh, that was
his. Yeah. He did that as a senior design project. So Eric Hurd did this recloser demo, which was part of his senior design for school. And it was cool because we just want to put up some light string and show like a tree maybe hitting the power line or something like that. And then maybe we could just like turn off the power a little bit and show people, probably won't take that long, right? So 400 hours later and a couple miles of cable later up in the ceiling. He was up and down the fork, the scissor left a lot. But that is a really cool one because a lot of times we start there and say, look, here's what's going on the utility side of the thing. And most faults on utility systems, different than inside your home, are temporary. So if 80% of the faults are temporary, we want to open up the circuit breaker and then test and close it back in. And so people then, you can see the light bulbs go off in people's heads. Like, that's why my microwave was flashing. That's why my lights flickered and I have to reset this or whatever. But it's a cool demo. And then we show one shot, like a lightning strike. And then we show 4 shots, too fast and too slow, where it can't clear the permanent fault, right? Temporary fault, permanent fault. And then we show coordination. So we show the recloser doing 2 fast shots and then doing a third one, where the line, hits and then there was a fault in the capacitor bank, and then we actually open it up twice, and then on the third one, it stays on longer and coordinates with the downstream fuse. Then the fuse blows and it falls down. And that one again shows, just like in these panels here, you have a main breaker, which you wouldn't really want to turn off.
Yeah, no,
Because you had to. You don't have to wait for the feeder breaker. So that's it's
yeah. What I find really interesting is you think about just think about the concept of a utility recloser.
Yeah.
You have a fault in the system. OSHA tells us to not close a breaker unless you figure out what the fault is, right? But on these transmission lines, it's like, yeah, boom, we're gonna hit it again. Boom, we're gonna wait. You know what? That tree's still there. We're gonna burn it off.
Yeah.
But they hit it like 3 times, and we've all experienced that. I'm sure. I mean, people who are watching this have experienced. The power goes out, and then it comes back on for a short, and then it goes out, and then it comes back on again. And that's that recloser up there on the poles that say, look, we're going to. Because a lot of times that fault can get cleared if it's a tree.
Yeah.
You've burned it away, and then boom, you're back up and running, and everything is fine.
Yeah.
But then when it's persistent, you have a bigger issue. Well, we would never do that now. Inside the building.
No, you don't close that breaker back. We talked about that. Actually,
Yeah.
one of the conversations you and I had that's related to that from a safety standpoint is, remember I told you about the electrician? He said,
yes,
he was working in a building downtown Pittsburgh. He said, he's just working ahead and whatever. And the power in the next door building went off. So somebody comes running over. He's like, hey, come over, help me. I gotta power back on, the power. He's like, well, I'm working over. He goes, oh, just come help me. We got to get back on. So he goes, well, what happened? He goes, I'm not sure, but let me take you to the electrical room. So he takes him there, 1,200 main trip. Okay. So the guy's like, so he said to him, he goes, here's the breaker that tripped, turn off your building. Guy's like, turn it back on. He's like, I'm going to turn on that breaker. He's like, no, just turn it on. We need to get power back. He's like, I'm not turning on the breaker.
Right.
Why did the breaker trip? Breakers don't just trip.
Right.
Okay. And so long story short, he goes, what else is going on in the building? And he goes, well, there's the only thing that's going on right now electrically is there's a guy up on the roof working on HVAC. Well, sure enough, the guy up on the roof took a Allen wrench across phases and tripped the ground fault for the main breaker to build.
Right.
Well, if this guy had turned on the breaker, that guy could have been in the equipment still, and he could imagine living with that. Oh, I got to hurry up and rush and put the power back on.
Turn the breaker on, you kill somebody.
You kill somebody, you go, well, the guy told me to do it. Well, that's never an excuse.
Oh yeah, no, absolutely not. Yeah. And that's something we're taught now, and that's the other thing. We're taught stuff, right? We're taught all of these fundamentals.
Right.
And when you're called upon, when you know better,
right?
It's like this. Another session during Shock Week I'm going to have with Vincent Barlow. He's talking about self-awareness.
Yeah.
Right. And when you have the confidence to say, no, I'm not doing this. So you're getting peer pressure.
Yeah.
You got somebody who's saying, you might have a crying bride, you might have a groom saying, I got a party, we've got a bunch of people out here. Turn that thing back on again to stand by your knowledge and understanding of electricity and training to say, no, I'm not going to do that. And that's what I think a lot of what happens here reinforces that and gives that confidence.
We talk to a lot of young people, and I say young people in the apprenticeship programs, people that are new out of college or whatever, but we always try to give them practical examples of why did you sit through this class and learn this? That's part of it, but really, here's what's going to happen in the real world. You're going to have to make decisions, good, better, best. You're going to have to think about safety. Am I going to be able to live with the decision that I'm going to make? And that's a big deal.
It's it's not as big as when you're making it if you don't think about it that way.
Right.
It's later on when you start thinking, wow, I learned this. Did I do that right?
Yeah.
Yeah.
So here's the thing, so we both went to the same college, we learned a good bit of stuff, but when you get out and you go, I don't know how much I really learned until you start to get the practical thing. And so I started teaching classes right away for utility people. And I was teaching classes to people that were 40 years older.
Yeah.
And what I learned right away, and I think I've tried to bring forward, is that I didn't have the stories, right? The stories help reinforce, and you do it all the time.
Yeah.
There's always a story that reinforces the topic. And if you could make it relatable, make it practical, just don't give me theory. Theory's okay, helps, but the stories help, right? I mean, you
Absolutely right. Yeah. And I get stories. Some of them are personal experience, but some of them, like that story, I know I'm going to tell that to other people in training classes. I'll say, hey, I was with Dan Carnovale. This is what happened in Pittsburgh, right?
Yeah.
And it's that you just carry on. And that's what IAEI is all about. IEEE is all about. It's about socializing all of our ideas and concepts.
Yeah.
And that's like what you do here, same thing. You get all in one room and you just start sharing your knowledge.
Yeah. Yeah, I think that's important, because early on I didn't have those stories, and I started stealing other people's stories, and then you start to make, then you start to have your own.
Then you have your own, yeah.
But it's a good way to learn, and I think that's what the experience centers are all about. I mean, if you could imagine, and people call it electrical Disneyland all the time, right?
Oh yeah.
But it's basically like, we have different spaces. Like we're sitting in the residential part. We talked about the power quality room, and we have the utility area, and we have an industrial space, and we have, kind of a oil and gas area. Especially in Houston, we have a huge oil and gas area, and we have big industrial stuff. You have a lot of the Kraus stuff and everything. And then we have a lot of areas where you show how things are put together, how they're built. And we even tour and sometimes walk through the main part of the building, which is where, the incoming service goes and how the wires come in from outside and everything. So all that stuff is really important,
to see that too. I mean, I know Larry here teaches a class in Cincinnati, and his classes, he has them go to facilities, right? And he tells them, okay, go look at the service, go figure out the square footage.
Yeah.
Think about how many lights are, like per square foot. How many lights do you think are in there? Then how much load is that? What do you think the size of the services needs to be? Right. So you're going through that whole, it's basically a design process, because if you haven't broken ground yet and you're going to have to quote a project, you need to have some level of understanding to figure out, how am I going to quote? How many light switches am I going to need? How many receptacles am I going to need? How many can lights? How much air conditioning?
Yeah.
How many tons of air conditioning do I need?
It's not something that, we had sort of the industrial design class with Sobaji, which kind of helped you a little bit, right?
Yeah. Oh, yeah.
But from again, he thought about it like that. And I think that's why I think both you and I have that passion for it, is he thought about the practical application. Like, okay, that's all well and good, but like, let's do a real plant and let's lay out the stuff. So that's cool.
Yeah.
I think the other part is that we do hear a lot of is the power factor correction piece, which a lot of people want to talk about claiming energy savings and all this kind of stuff. And there's a lot of the false energy savings.
Yeah.
And power factor correction absolutely works, and it has a purpose, right? I mean, we make capacitors, we make harmonic filters, we do all that. But one of the biggest things that I run into here, we do testing, training, and demonstrating. Testing is important. So I'll bring in equipment and test it for people and show, hey, does this thing really do what claimed, right? And that one we have in the residential part over here, like the little demo there where we turn on the motor and show, there's, almost 6 amps of current. Then we turn on a capacitor and the current cuts in half. And then somebody out there is going to go, well, you just saved 50% of your power. And I'm like, no, let's put the meter on watts, right? And the watts don't change because a motor running unloaded is mostly inductive. And so you explain imaginary power, imagine that, right? So it's just, that's again,
that's
one of the most difficult things to explain
is imaginary power. You're absolutely right. And I remember the first time, I'm not sure which professor in school, when he said, okay, imaginary power, I called home and I told my dad and my mom, I was like, I'm learning about imaginary power. And he's like, what am I sending you to school for?
Yeah.
But it's so true. Yeah. But to be able to visualize it, because we talk about the power triangle, right? And we talk about it. I've done a program on power factor correction. You have a video.
Yeah, we have a couple. We have one that's called What is a VAR? So that is, it's a good video, because we actually did it during COVID. So we did like a Teams call and we had a bunch of people just talk individually. But we do a lot of the analogies, like the beer analogy or There's 6 or 7 different ones. And I think the analogies are good because you can describe something that's like it. But the problem is there's nothing that really can explain, again, the magnetic field and all that until you physically see it on a meter, showing the motor. Here's a motor, unloaded, loaded. Here's real work. Actually, the hand crank generator.
Oh, that's right. Yeah.
Right?
Yeah.
So the hand crank, we have people over there. If you've never seen it, we'll show you a picture of it. But basically, it's basically you turn this thing and I go, okay, now how hard is that? Well, it's not hard at all, but there's nothing turned on. So you basically are generating voltage with a little generator. Overcoming friction, just very little resistance. We throw on a 3-watt LED light bulb. So it's a little bit harder, but you can feel, so watts equals work. So the more work you do, it's a little bit more work. Then it's so funny because you get these big guys when they're, they're cranking this thing away. And then we go from 3 watts to just 25 watts, just a 25-watt light bulb. And they're like stopped in their tracks. Then they pretend it doesn't hurt and they go,
Yeah.
But like, here we are putting all this power into 2 different types of light bulbs. That's why I blow up all the light bulbs, because we don't have any of the incandescent ones around. But the 25-watt light bulb is like literally like more than 8 times the amount of work that you're doing for the 3-watt.
Sure.
And so recognizing from start, you're creating a magnetic field, just overcoming friction. That's the VAR part.
Right.
Then you go to a little bit of work. You can unload a motor, maybe just a little bit overcoming friction. And then you go to the full work. And then we do things like we charge a supercapacitor, which is like a small, short-term battery kind of thing. And that was the other thing that I learned that was funny from college was, remember when Sabaji used to send it, he'd say, oh, I just sent that kid to the store, Radio Shack, for a 1 farad capacitor, and he would laugh. So some of the capacitors that we have here are like 100 farads. So
wow.
So most of the stuff you think of microfarads and all that, but again, back in when we were in school, it was almost like it was literally a joke. Like, it'll make stuff like that. Yeah. Now you do, and you can see how you can store energy. Yeah, it's pretty.
Yeah, and then you can. That's how you take a break, right? So you're doing that, and then you let the battery take over. You go like that, and you get back in there again. Yeah,
exactly. No, it is fun, and the other thing we do with that too is we charge up 3 different levels of supercaps: a 10, a 25, and a 100, and then we show like the duration, so the watt hour or the amp hour or how that relates. So the 10 will run for just a few seconds, and the other one will run the 25 will run maybe for 4 times that. And the one that, it takes longer to charge it up, but you're going to get all that benefit. So the kid that fixed the wrong one is sitting there, going on.
Yeah.
But it lasts for a long time.
It lasts for a long time. I like it.
Yeah. So, the other one that's in that same area that we talk about is the breaker demo.
That's the selective coordination one.
Yeah. And I like that one for a couple of reasons. One is, we talk about thermomagnetic. What's thermal? What's the magnetic part? How do we set a breaker? So the thermal part is overload. So we put a 225 amp breaker, I think it is, and we put maybe 700 amps through it. And we have people watch and say, at about 10 seconds, that breaker is going to trip. So if you had the trip curve, you could line it up and see exactly where it would be. And sure enough, it trips. And then we crank up the current, and we have a little fault initiator essentially, and it generates real current. So we can go up to about 3,000 amps. And,
oh wow, low voltage.
And it'll crank, and so it's like a high current test.
Yeah.
But essentially, what we do is, as soon as we initiate the fault, the breaker trips, and then you show sort of that instantaneous or magnetic,
absolutely,
trip. And then we do a couple breakers in series, and we show, one breaker tripping, like downstream of a main, for example. Like again, in your panel, you want the main to trip only after the other one doesn't trip. And then we show miscoordination. You say, well, what if somebody jacked these all up? And so you could have the main trip instead of the feeder, or you could have both trip. And there's,
you can change the settings.
Yeah. It's again, most people don't get a chance to, play around with breakers like that. And the other thing that's funny is the first time I always ask people to reset the breakers in the middle, they don't know how to do it.
Oh no,
you have to experience that.
Yeah.
How do you do it? Turn it off and then turn it back on.
Yeah, it's like counterintuitive. It's almost like Windows. You've got to go to the start to shut down.
Yeah, that's a good point.
Yeah.
Never thought of that. That's a really good point.
Because you got to go to off to turn on.
Fair enough.
Yeah.
Yeah, I've never thought, but that's exactly what you have to do. You turn it all the way off. And then, today especially, there's so much around vehicle charging. So we have different types of vehicle chargers, like the wall-mounted ones. We have
I love the breaker
ones.
Yeah.
This is a vehicle charger. I mean, when you think about this, and then put it in a panel, and we put it so.
Or even so one of the things that are going on right now is, and we're arguing. Well, I made a public input to panel 12 for a new article for charging boats.
Okay.
So there's electric boats, but it doesn't meet the definition of electric vehicle. So I'm sitting there thinking, okay, how are we going to do that? I mean, how are we going to, and this, you could put this into a power pedestal that's already out there, and boom, all you need is the inlet, right? And then there's the debate on, okay, what inlet does a boat use? Is it the same as the J 1772 interconnect, or what is it? And but it's just amazing how, there's electric planes.
Yeah.
There's electric boats. There's farm equipment. John Deere, I think, is coming out with a backhoe and
we've seen excavators and stuff. Think about so one of the companies we were working with out of Buffalo, they were doing an excavator electric, and we said, like, well, why would you do that? Well, first of all, it has a lot of power, so you could do that. But secondly, think about this: like, if a person's down in a ditch and they're digging, all the fumes from the diesel typically accumulate. So every hour they got to come out of there like that. Yeah. And then there's the noise, right? Yeah. So super noisy. So they can run these electric ones inside a building with no fumes, obviously. Yeah. And it's really funny when you have, the beeper on a big, truck or whatever. Yeah. They're so loud, but that's to overcome the loudness of the.
Yeah. It doesn't have to be that loud.
So when these things they're like way over the top loud, and I think they're going to probably say, "Hey, we don't have to be that loud."
But I've heard, like, on farm equipment, they don't like the fuel and whatnot.
Yeah,
because you don't have the fuel out there in the field, so it doesn't enter the ground and doesn't make the soil. It's a big deal. Yeah,
yeah. So they're getting better and better. So we do the breaker ones, we do the all the way up to the DC fast chargers, and then we have like the solar canopy outside that has. We've got
windmill out there too.
Yeah, we've got the windmill, we got the solar, we got the vehicle charging underneath the canopy. We're putting a switchboard in there that actually, puts a bunch of these breakers together. Then we have the pedestal ones in front. So
that switchboard's going outside.
It is. They just put it in today. Yeah. And,
I saw it all roped off, and I was wondering why I didn't get the park there.
Yeah.
Now I know why.
Yeah. So think about this as a practical application. Let's say you have pipe in the ground already, and we had a 200 amp feeder going out to the solar canopy for loads or whatever we wanted to do. At first we were running it at 208, and we're like, okay, we can put X number of chargers out there, right? And we're like, wait a minute, what if we use the same wires, because they're 600 volt rated, right? And then we take a 480 volt input and put the transformer outside.
Oh, now you can lower the current.
We can lower the current or just add more chargers. So now we can like, with the ratio of 480 over 208, number of chargers out there now, and really so this is what we're talking about, again, from a practical application, parking garages, stuff, and then you can extend the cables for these breakers like up to 150 or more feet. So you're essentially running conduit up to wherever you want, and you just got a little junction box, and that's it.
That's pretty cool.
It's a cool application, and the fun thing, Tom, like, I always tell people, like, if I didn't learn something new every day, I would not want to do this. But it's been over 20 years now. It's like, it's a blast. And I think now, part of that excitement is seeing people new in the industry learn about this stuff. That's what that experiential learning part is. It's all about.
As in even like you said, doesn't matter how old you are or how long you've been in the industry.
A lot of this is new.
You're gonna learn stuff, especially now. We're in a world of electric vehicles growing, photovoltaics. We got electric vehicles that want to power the structure too.
Yeah.
Okay. The power's not just going this way.
You
got vehicle X. I never forget it. I heard V to X, V to H, V to G, and I'm like, just spell it out for me. But there's so many different configurations. It's just phenomenal. And then you got it's one thing. And in fact, I was on a phone call the other day and somebody was giving block diagrams, and I'm trying to figure out what codes and standards are impacted by this, and I said, I need a diagram. Okay. I'm like I say, I'm a visual person. I'm a visual learner, and I think better visually. And then once you start having diagrams, then I think everybody's eyes open up. And I had a block diagram. They came with a block diagram. I said, this is not what I need. I need to show me, how are you going to get from here to here? And nobody on the phone could answer the question.
No.
And I'm like, okay, guys.
Yeah.
You understand why I'm asking the question, right? Because and then you take that and you go out here in the front and say, okay, now I've got to actually pull wire. I need lugs. I need to do the calculations. I have to make sure it follows the code. What sections of the code do I need to follow? It just gets more real the closer you get to the boots on the street.
Yeah.
And the block diagrams don't work. And so,
yeah. And I think those projects really open your eyes to those things. Like,
sure,
we put in the energy storage and the energy aware UPS over there to compensate for the DC chargers as well. So we have, let's say the DC charger takes up to 150 kilowatts. So we don't want to hit a demand on our buildings. So what happens is we actually have batteries that we fill up overnight on the big UPS that has 240 kilowatt hours. And then we discharge it while we're charging the Ford Lightning over there. It's a 90 kilowatt hour battery.
Cool.
It keeps it nice and flat, right at 70 kilowatts for the whole.
Yeah.
And it's one of those things that, nobody really thinks about till you actually have an application where it's
Right. Yeah.
So
That's pretty smart. Yeah. And you got, like you said, you got a plan. You know what the issue is, and then you know how to address it by coming up with all different ideas.
It's got to make sense financially, which I think I might have told you. So the microgrid that's out here, we have multiple different sources like solar, and you said wind. We put that into the residential part, but the solar, the batteries, gas generator, natural gas generator, and the utility and super caps all into the microgrid. And I think I told you my story about my solar on my house. I kept saying like, yeah, I like the idea, but I'm not gonna. So my brother, who's a pharmacist, of course,
but you stay in your lane.
Yeah, I told him, I said, stay. He goes, oh, you're gonna put solar in your house, Dan? I said, no. I mean, I talk about this stuff all the time, but it doesn't make sense quite yet financially, blah, 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 whatever. I put solar in the building and it's just for them. And then, I said, stay in your lane. And so I started to look. He goes, well, have you looked at your bills lately? And I could not believe how much I'm paying for kilowatt hour. I'm paying like 23 cents a kilowatt hour.
Really?
I kept telling him, look, that's like 12, He goes, look at your bill. It was like 23 cents a kilowatt hour. So I just put on a new roof. I put on solar, and my payback's like 8 years minus whatever SREC credits I can get. So
sure,
not a bad deal. And honestly, like last month when my bill was zero, I was like, this is pretty cool. Thanks, buddy. But I'm not going to tell him he's right. So
no,
cut that part out.
Yeah, I'll cut that out.
Watching.
Yeah, I'll leave in the stay in your lane.
Yeah, no, but again, like talking about microgrids, talking about all these distributed resources.
Yeah.
It's one thing to talk about them, and then there's the practical side, and it all comes down to financial. No matter what it is.
Oh yeah.
At some point, it's a financial or a safety story, right?
Yep.
Or a risk of avoidance kind of things, which is also financial. So to me, it was like a real eye opener when you start looking at why would you put a piece of equipment like a vehicle charger or batteries or whatever in? That's the other cool part that we have.
That's pretty cool. So you got a lot of alternative energy and interconnected practical installation, all that good stuff. And that's good just from showing it. But do you do demos with it as well?
Yeah. Oh yeah. So we have a vehicle to grid demonstration. That's not really here yet, but we want to show people what could you do if you're, actually a couple of years ago in the Super Bowl, they were like, oh yeah, you can take your truck and plug it into your house and light up your house. Well, it doesn't have that transfer switch or this manual transfer switch built into it. So
that's right.
People have to realize, just like when you put in a generator, you're not going to do that because it's not safe, and nobody's going to let you do that from a utility company. So we actually are obviously working on stuff that you can make that possible with, but we make it a safe demonstration here and show, look, I mean, you got this vehicle, it's already charged. So like, we could use part of it to back up your house, or maybe you're out, at hunting camp or something like that, and you want to just show like how can I power my camp overnight or whatever? It's just simple stuff.
Absolutely.
But it's definitely showing technology in a way, maybe like with the smart breakers and stuff that maybe people haven't thought about before.
I love these things. Yeah. No, I like it. I like it. Yeah.
I mean, we have some of the other stuff that we show are like with the VFDs.
Medium voltage.
Oh, the medium voltage. Oh, yeah, yeah.
I love that's brand new. I just saw that for the first time yesterday.
So actually what was interesting, and you saw it in there today, we had some of the old people in there racking out a breaker, racking in a breaker.
Oh, yeah.
It's like, here's the wrench. You said we should make her dress
With the 40 cal outfit.
which I don't disagree with. I think that would be the real test, right?
Yes.
And then we turn on the heat in the room and see if you pass out. But no, like racking in a breaker and then showing new technology of automatically racking it out.
Yeah.
And the other thing that was, I think an eye opener for these guys that were in there today was that one breaker in there could feed. I said, how many homes do you think it could feed with this? And it was like, 20, 30. And then one guy, I thought he said Milwaukee. And I go, yeah, you're close. And there's like 25,000 homes, right?
Yeah.
So when you start thinking about the amount of power that goes through some of these big things.
No, you're absolutely right. No, but when I said medium voltage, I'm talking about
the
spark
gap.
the spark gap.
So
that has so many great examples from an educational perspective.
Yeah. No, I wasn't thinking about that, but talking about the medium voltage breakers and the vacuum bottles in it is what made us think of the spark gap demo. So
really?
It works here. Well, every day we talk about all these different. You asked earlier, like, how do we come up with demonstrations? And it's always iterative. We're like, what if we could show this, and then we do that, right? So the recloser thing was like that, but this one was, we always do this. We go, voltage flashes over in air at 10,000 volts per centimeter. And then we go like this, and nobody knows what a centimeter is. So we just do this, right? So an inch, you go, whatever. But then we go, no, here's a vacuum bottle, and it won't flash over in there as a real, because it's even a smaller, it's like a half a centimeter. Yeah. How does that work? Well, because in air, we're literally almost like burning the air, ionizing the air. So then we said, well, let's build a demo where we have two electrodes and we can expand them and contract them. And then we show a gap. And so we start with a big gap, and we ask people, how much do you think is going to flash over it? There's some people,
How many voltage, right?
yeah. What's the voltage? And I can't remember yesterday. I think one person said 120 volts, or like a bit higher. So he said 5,000 volts, or like, And then so Seth turns it on, or I can't remember. I turned it on yesterday, and it was like, well, we're at 10,000 volts, so it's definitely over that. And we don't tell them the 10,000 volts per centimeter yet. Run back to that. But then at that length, the first one we do is about 85,000 volts. So it's a big crack,
Oh, yeah.
But like you said, there's a lot of cool things to be learned there, because we do it with a high pot set. And the current limit on that high pot set is 25 microamps. Okay. So 25 millionths of an amp.
Yeah.
So when you think about that, you go, okay, I've got a transformer in my factory that can deliver 25,000 amps or 50,000 amps.
Oh, yeah.
A ton more current than what we're talking about here. That's why stuff explodes, right? So you see this flash, it scares people a little bit from the bank. And then we do another one where the gap is smaller. And the test set doesn't trip out because it doesn't go into that current limit of 25 microamps.
Sure.
But what we do there is we say, okay, now we've got this arc going on, and then we go, well, how can we kill the arc? We can expand the gap, which would be like tripping a breaker, opening it.
Sure. Yeah.
Or we could reduce the voltage, which may or may not be practical, but we reduce the voltage and then we trip the breaker on the test set just to show the difference. And then we explain a lot of what we do, are switching devices like breakers, fuses, contactors, all of the above, right?
Yeah.
It's such it just reinforces the concept.
Yeah. But so when you say about the breaker and that, you're talking about the contacts, but the other thing that I think of, because I know in some of the stuff that I've tried to talk about online or whatnot, we have on some of our breakers and some of our motor starters and whatnot, they'll have these fins.
Yeah.
Okay. And we talk about things like creepage and clearances.
Right.
So in some cases, I might have for the, like, as you go up in voltage, you might have a termination here, and you have a barrier like this,
in there,
right? So you look at how many inches between this terminal and that terminal because you can get the flashover between the terminals. So you need space, and you might need the barriers to prevent that arc from occurring from one to the other. So, and when you demonstrate that, and it's like, okay, now I get, I mean, when I'm dealing with 120 volts, I don't have to worry about the space in between here. But if I'm dealing with higher voltages, now I have to think about the creepage and clearances and all the other good stuff. And
well, that creepage part is, remember the one person brought it up today. We talked about the insulator shape. Why is an insulator shape like that with the in and out?
yeah,
It's that creepage distance. So instead of being from here to here, it's like literally that longer path. And so we talked about an accordion stretching it out.
sure.
And as dust would collect on a straight path, it would flash over as easy if it goes around that.
Now, do you think? So there was an example. There's a YouTube video. I'll try to put the link down below or whatever. But there's an example. There was a training video for scissor lift, and the individual it's like a rental agency, and this individual's job was just to take the scissor lift in the backyard after they get it back, clean it up, oil it, and they have to take it up and bring it back down again, just exercise, make sure it's good for the next person. So apparently he went to the farthest part of the yard, and then when he went up, he was not touching, say, a 348 kV or whatever it is line, but he was close enough that there was an arc over and it killed him, right? So when you look at that and you think current travels through air, now that's an example, a real world example where it hurts someone.
Yeah.
What you're doing is showing what can happen. And we go to 70E. 70E has a table that tells you for shock boundary, there's 3 different boundaries. There's the restricted zones, restricted boundary, limited approach boundary, right? So, and like when you start talking about those boundaries, you're really thinking of shock and whatnot, right? But you'll see in the one table, there's a column for a fixed energized part, and then something that's not fixed, meaning you have maybe a conductor that's swinging.
Okay.
Like a bare conductor or whatever. Yeah. So where you have we're moving like a power line or whatever. Yeah. So and they give you distances, and and what you demonstrate there. I mean, you could use it for a 70E discussion.
Yeah.
You can use it for a product design discussion to try to tell why you have terminals, how far apart they need to be for the insulator. There's so many applications. I absolutely love that example.
One of the things you bring up with that particular one, it's over by the transformer in the substation, is we talk about the BIL on a transformer.
Oh yeah,
the basic impulse or insulation limit. So, and then we talk about lightning arresters, and we say, well, what's the lightning arrester's job? Is to get it below whatever would be acceptable by the device, so that it's not going to fail on that BIL rating, which is a high speed, high frequency thing. But at the end of the day, like, people think, okay, I'm putting 34.5 kV in, and I'm getting 13.8 kV out. That's all I have to worry about is that voltage. But there's other voltages that could exceed that, which is why you have to build in those safety margins and why the spark gaps are so important. Because even on a 480 volt system, we know that as soon as we initiate an arc, it's going to be hard to get it apart. And we used also the Jacob's ladder analogy to show, we have a Jacob's ladder here. Yeah. And Seth just did a video on the spark gap thing, so it might be interesting to link that one.
I'll link that one too.
But it talks about the Jacob's ladder. So what you do is you have a little spark gap down low, and you flash over, and then you stretch the spark gap higher and higher until it finally extinguishes itself. That's how a Jacob's ladder.
That's
works.
right. Yeah.
So as you initiate the arc, you have to be close enough within that 10 kV per centimeter. And then once you do it, you stretch the arc. Well, the reason I bring that up is as you're burning, and like you said, with arc flash and all that stuff, as you're burning even at 480, that doesn't have to follow that 10 kV per centimeter anymore. All you got to do is initiate the arc, and then you can stretch it. And once you create a current path until it blows itself out
That's a valid point, because when you do that, you have it in air.
Yeah.
You're creating a larger voltage to get it to go.
Yeah.
But if you initiate it.
Yeah, you can stretch it.
Now, yeah. Interesting.
So maybe one of the next things we'll do with that demo is to
put a little piece.
Start the arc. Well, start the arc.
Yeah.
And then start to stretch it to see how far it goes before it breaks.
Yeah, that would be cool. You could probably do that with a little piece of wire or something to just a hair. Not mine. I don't know where we're gonna find hair in this place. Well, that's so funny. We have to hire someone. Yeah, I love it. That's fun.
No, so, and I don't know if I talked about the other one that's really, I think, a good one is the water analogy one. Now, of course, it's leaking right now because I'm good with electricity, but not with water. I can't do plumbing.
You and me, but I can.
But you know, that one video that we have on the water analogy where we have Santino and Kendall, you know, in there and explaining how electricity works. We always, again, you asked, how do we come up with demos? We used to talk about a super soaker squirt gun, pump it up, build up pressure, voltage, pull the trigger, squirts the water, you create current flow.
Yeah.
So we're like, what if we could make a demo out of that? And so we have a voltage and current kind of thing. And then we do Ohm's law. We put valves, which act like resistors.
Yeah.
And then we even have like a little surge protector thing on there that has a relief valve. We have a one-way check valve, which looks like a diode.
Right.
We have a storage tank, which looks like a capacitor or a battery.
Yeah.
We have a flywheel or gerbil wheel, which it takes a little bit to get going, but then so it's like a motor. So starting current, running current, and inductance or that imaginary power. And then we have current division, you know, Kirchhoff's current law, and then we have Kirchhoff's voltage law.
Which you actually have meters on it, right?
Yeah, so we have meters, so we can show. We show it in gallons per minute, but basically you have 4 gallons per minute in, 2 gallons per minute, 2 gallons per minute.
Yeah.
And then what we do is we turn off one of the valves on this side, slow it down, and then it gets bigger.
It's 4
so
gallons
it's like
a minute.
4, 3, and 1, and then 4, 4, and 0.
Yeah.
And then Kirchhoff's voltage law, which is if I've got voltage from here to here, and I put 2 resistors in series, I've got a voltage drop across one and across the next one. So the more I turn up, and it's additive. So it's just a very visual thing. So we're getting it rebuilt right now, but it's, I didn't know that plastic warps like wood. I had no idea. It literally starts to do, and so the glue and the stuff that we were holding it together worked for a long time. And then we tried a different type of plastic, and then it just started moving, and it was just one of those nightmare things that, you know, water when it leaks a little bit,
especially in a place like this that has a lot of electricity.
With electricity. Probably good thing we have ground voltage.
Yeah, that's true.
But that stuff, and I mean, when you think about switchgear, whether it's, you know, explain the difference between switchgear and switchboard.
And I love the description. Like we talk about here, you got a service, you got the sub panel or a panel board that's downstream. Talk about the bonding differences between the two. And you're physically showing it.
Yeah, like that one, especially because you have, you know, most people think, okay, maybe I'm going to drive this screw in the sub panel over here. Well, no, don't do that because you have a main load center.
Right.
And oh, by the way, don't do that because you have a transfer switch. And oh, by the way, don't do that because you have a breaker on your meter.
That's exactly right.
You back up to where would I put the neutral to ground ball? And it would be, in this case, it would be at the breaker over there by the main meter. And then if you didn't have that breaker there, it would be in the transfer switch. And if you didn't have that, it'd be here. And
you know what I need to do? I'll tell you what I need to do. When we were talking about this, I would love to make up little signs and be able to label, like when we talk about the bonding, 250 to 1, whatever.
Yeah.
We talk about like the service equipment.
Right.
Put the article and the sections. I think that would be a really cool. That would be like codes and standards stamp.
Yeah. But I liked your idea earlier. You were saying we should make a hologram of you, and you could float around and just tell people what it is. We can do that.
Yeah. Why the heck not? It's and it's
You know, the one that I think is a newer one that Seth came up with recently was that maze one back there.
For the thermography?
Yeah. So we were trying to show, like a loose wire demo was our initial thing. We'll just make a loose wire and panel, and it works and doesn't work depending on how much current you do and all that. So it's not consistent enough to show consistent, you know, demo. We can show obviously heat, and heat's a bad thing, but what he wanted to do was show sort of the path of current. So he made up a maze, and then he did this in Excel, which is crazy. But he made like these little blocks, and they connected them all together. And then he made one of these mazes that you would trace with a pencil normally. And it actually says PSEC, Power Systems Increaser. It spells it out. And then he accidentally made an extra path that goes up and around a little bit. And so we always say to everybody that comes in here, we say, current flows to, and they go, the path of least resistance. And we go, no, current flows to all paths, but it favors the path of least resistance. And so that's a great example of showing how, yeah, it goes through the main path, but it also goes around that little path, not as much. Yeah. So I'm almost glad that it kind of worked that way.
Yeah, and it's a good teaching. Here's the thing: I always say, and I make a mistake. I make mistakes on videos. I make mistakes, whatever. And when somebody will say, well, no, it's this. You go, see, that was a test.
Yeah.
It was a quiz. It was a teaching moment.
Thank you for pointing that out.
Thank you for pointing that out. You get the little star. But no, that's a really good example because you do the thermography and you can see, obviously you see PSEC, which is kind of cool too.
Yeah.
But when you take it away, you don't see anything, right? You can't tell. And it's a really good reason it supports NFPA 70B, where you talk about thermography on an annual basis and like determinations. And then you've got in this room here, you've got the troughs, the iris scan windows.
Yeah, windows for switchboard.
I never knew they had for panel boards.
They just replaced the I saw the dead fronts on not the dead fronts, but the gutters.
Those are, and there's all different shapes out there. There's the long square ones, and then there's the skinny ones for the troughs. There's just so many. But thermography is another one of those mysteries because it's like, well, what's good and what's bad?
You can't take the doors off anymore. You really can't. Now, most equipment you're not going to be allowed to, or you shouldn't because of safety reasons and arc flash and stuff. So having windows is a huge benefit. And the thing I like about the new windows too is you can see through them. So you literally can shine a light in there, or you can have a light. Ours are backlit because we have special stuff. But you can look inside there and you can physically see what's going on and take a picture, and then you can also thermally see what's going on.
Absolutely.
And that's it. It's always going to be those. Remember, so we have those little carts for the people.
You got to do that. Put it inside so when they arrow down, you can see PSEC.
Yeah.
Anyway, go ahead.
Well, no, but that would be a great idea. With the carts that we had the students working on today, I don't know if you got any pictures of that.
Oh, I got a video of that. Yeah.
So the cool thing about that is we try to show people like, okay, dude, just wire up a residential panel, wire up a simple breaker, switch, and a receptacle, right? Two receptacles. And one's a ground fault, one's a standard. And like we talk about it, but most of the time, because we're coached a little bit, they get it right. But there was one today that they had something wrong, and we didn't know exactly what it was, but somebody had cut the little bridge on the hot connection on the back of the one,
separated the top from the lower,
from the receptacle.
Yeah.
And then we've had people put the wire, without stripping the wire back all the way, or maybe they stripped it back, but they jammed the insulation underneath the screw.
Yeah.
So it didn't work, or they short something out, or, so we'll trip a breaker. But it's really cool. And I think like people that have been in the industry for a long time that have never physically done that kind of work, I cannot tell you how many people are like, cool, I didn't realize it's still, first of all, it's not simple to make it work. And then secondly, to make it look good is really difficult.
Oh, absolutely.
So you really gain an appreciation for an electrician that's good at their art,
Yeah. I was talking to someone who was in the training world and building, apprentices and whatnot. And he said that you would be amazed the number of kids, I'll call them kids. I'm 50 something. And so when they're kids and they come into the program, they don't know what a crescent wrench is.
Yep.
They don't know what channel locks are. Phillips versus a regular screwdriver, right? So if you, and you can't blame them, because they haven't had that experience. So, but you have to understand where you're working from, right? So you never know who that student or what that person's experiences are.
Yeah.
And the people that you had here are engineers that come out of engineering school. I don't know if any of them, have that level of I don't know if they know, they probably know what crescent wrenches are and things like that, right? But you don't know, right?
No.
And so they're out there working on this, and it's comical because I liked Michael told them, he says, those of you who have done this before, step back.
Yeah.
Give someone who has never done this before a chance to walk through that and go through that motion. And like you said, you look at this, you think, well, I know
How hard can it be?
to me and you, it's obvious. Okay, yeah, the stuff that's not covered with this white or black needs to go under the lug. How hard can that be? But if you've never done it before,
Yeah.
and you're experiencing it for the first time, it's like, wow.
Well, even knowing which side of the receptacle is the hot black wire and which side is the white wire.
And all of that,
Yeah.
my contention is all of that is 70E training.
Yeah.
Because people, I think, have a false perception. They think 70E training, I'm learning how to don equipment and things like that. I'm learning to recognize the hazards on it could be just a receptacle.
Yeah.
If you don't know what is the hot, what's the, and you may not realize that those are energized.
Yeah.
Right. You may think that, well, all of this is protected, but no, it's not, so all of that is safety training. And you may have, you never know, one of these individuals could be in their home environment or purchase a new home, like in my home. I bought a new home. I went downstairs downstairs. I went in my closet. There's a panel board with no dead front.
Oh, wow.
And there's hangers right in front of it.
Yeah.
And you go, wow.
How did this happen?
How did this happen? But if I did not have a level of awareness that don't touch the copper, that this is dangerous, you may have hurt somebody.
Well, I don't know if you remember, this was years ago. We had a photographer out in one of the sites, and somehow I don't remember what the story was behind it, but he saw the blue bus in the back of switchgear.
Yeah.
And he said, "What's that blue piece of wood?" And he went to grab it. We're like, I wasn't there at the time, but like the people that were there were like, no. And apparently it shocked him and he fell back and didn't get killed. But why would you be like, but you like said, people that don't know, they would maybe just say, "Oh, look at that pretty piece of wood."
What the heck is that?
Yeah, because electricity, again, goes back to the magic thing, right? You can't see it, but you certainly feel it and all that kind of stuff.
Absolutely.
But, speaking of the tools, it's really funny because I told a bunch of those students today, or those young people today, I said, the biggest issue I see with interns, and we've had 25 of them here, is not tightening down the screws, right? So they don't tighten them down, torque them down, or and so I always tug on the wires and whatever, and we show them, like, a lot of times they just fall out. So besides doing it, but I did have a couple students a couple times where they didn't know how to use a socket set. So it might be, we were putting solar panels together, end of the 1K to the socket, and he goes, "This thing doesn't work." And I was like, "What do you mean it doesn't work?" And he goes, whatever, and flip the switch, and he goes, "It still doesn't work." I'm like, can't help. Go to YouTube. No, but I mean, it's not really their fault. And, I mean, once I showed him once, he got it. But it's just one of those things that could, if maybe you didn't spend some time with a parent or a friend or somebody that could show you that stuff, it's not necessarily intuitively obvious.
Absolutely.
And especially with electrical tightening,
torque is so critical. Absolutely. Yeah.
Where the thermostats, all that come into play.
Absolutely right.
I think the distractor today of being on phone or something like that, we have one of our videos about that, but say you get a phone call in the middle of doing some work and you forgot to tighten that last screw, and I think we're all done, shut it up. And that happens probably a lot. People get so distracted with different things that probably wasn't as big of a deal 20 years ago. And so, or maybe you're just so busy, you get called to a different thing. But loose or missing connections, or just like they put the wires in but forget to tighten them down.
Yep.
Such a big deal. And that's where the thermal imaging comes into play.
Absolutely. And then you need the iris scan windows so you don't have to take the dead fronts off.
Yeah.
And expose electrical workers to, if you're doing it annually.
Yeah.
And you have to draw a current through it.
You have to. There's no point in doing it if there's no limit.
Yeah. So, I mean, it just makes a lot of sense. And there's a lot of tools, a lot of things available in that world. So always before, I learned this working on my vehicle. If you don't, you got to, I go down to, whatever supply house where they sell vehicles. I'll go down there and I'll talk to the guys, and I'll say, whether it be a nap or whatever, this is what I'm doing. What are you making that makes my life easier? Yeah. But plumbing is a good.
Oh yeah,
very sure.
especially
Like
I don't like plumbing.
Yeah, I hate plumbing, and I've sweated a lot of joints before, but they come out with new technologies, and you're like, wow, they can make your life easier once you know the new technology. So that's why you go down to your supply house, you go to people who are knowledgeable, and you say, hey, this is what I'm doing. You got anything to make my life easier? And
well, and that goes to the receptacles. We were talking about that today with some of the guys that were wiring them in, and the one girl asked me, she said, well, I thought all the receptacles, you had to like twist a wire around it and then tighten it down.
oh yeah,
So that stuff. And I'm like, no, there's better ways to do it and more consistent ways to make it tight and everything.
absolutely right.
And, but yeah, there's just, I don't know, as you can tell, it's fun. And but between here and Houston, we just have so many demonstrations of stuff, and we're always looking for new ideas. So, I mean, I just, anything that even anybody out there has ideas.
Oh yeah.
Demonstrations. I mean, I'd love to build the next, really cool electrical demonstration of stuff.
Yeah.
You and I talked about things like DC power and things like that.
Yeah,
We do some things in that space, and lots of different.
If you have any ideas on what you would love to see demonstrated, shoot me an email. You go out to my website, thomasdimitrovich.com. You know my email address from the YouTube site here, so you can check all that, and then I will make sure that I put he makes videos, cool videos on most of the stuff that we have in this facility. So I'll have the link to, what is it, Eaton.videos?
Eaton.com/experience.
Experience.
On that website, you can find the Experience Center videos, but also on YouTube, there's a link. Actually, if you go to that link first, there's a click on the bottom of the video channel to the YouTube channel. So you can have all those. So there are, I mean,
yeah,
you can definitely find them there. Or I could give you the link directly for the YouTube channel. But to us, it's interesting, because I always tell people I got drafted into marketing, right? So I was an engineer that was like, and they go, well, you're going to be in this marketing group. I'm like, no, I'm good. I like the technical stuff. And they're like, no. So anyway, found out that I can do really cool stuff in marketing and still do teaching and training and all that. But one of the things they told me, and you and I have talked about this before, is never make a video more than a minute or two, because nobody will watch it. And so you and I should chalk up the numbers of views on your videos and our videos.
Sure, yeah.
And I think it would be interesting to see how many of our videos are less than a minute. 0. And then how many views we get compared to what's out. Sure, right. And it's not.
Here's the thing with YouTube.
Yeah.
They can go fast forward.
They could go fast forward and you have chapters. So what we've done is it's more efficient for us to make a video on arc flash solutions. And then you want to see the arc quenching device, you go here. You want to see, So okay, you can make a minute video. So don't disagree that short things are good for that point, for the video point. But like having the full story to me is more interesting because, and you do this all the time, but I think like if you can explain from start to finish why things are the way they are, you fill in the gaps. People are going to go to the part they need. Sure. Then they might also notice something they didn't know. And one of the things that we do with every visitor, we did it here this morning. These guys are here for 2 days. Tell me something you learned that you didn't know before. And it's amazing. We always make sure that they all tell something different. So if every single person that was in there told us something different, and so it's the same thing as going to these videos. When you find that you're watching part of it, everybody has a different view of it, right? Your own perception. And because they have a different experience they bring with them.
Yeah. And they can listen to these. So I have a lot of people who watch my YouTube channel that say they have it playing in their office. And they're working on stuff and they're listening in the background because I'll go for an hour, like I do IEI News Lives every Tuesday, 12 o'clock Eastern, be there. Okay. I do 1 hour and they'll say, I'll play it. Steve Fromming up in Wisconsin. He's out on his tractor. He's got his earbuds in and he's cool. He's listening. Right.
Yeah.
So you don't have to necessarily watch the video. You can listen to the video. And when you hear something, you go, what are they showing? Then you go over it because it's always going to be there. So, I agree. Everybody has a short attention span. So, but to hear that story all the way through makes a big difference. What did we miss? Did we miss anything?
I think we covered a lot of it. I mean, there's just a ton of things that we have, and I think we have over 250 videos that are our systems experience center videos, and we're always making more. We have a lot on harmonics. If you're interested in that, we have frequently asked questions on that. Probably about 50 videos there. But like, I mean, we could go on for days. Like we used to have just that one room. And now,
Oh, I know.
we have all these different areas. We're adding new switch gear. Oh, we're bringing a new demo this summer. I'm interested in trying to see how this is going to work out. But we did a little demo with transformers. Talked about a little bit about this yesterday. We took 3 single phase transformers and we made delta Y, delta delta, delta YY, Y delta, and then we did split phase. So anyway, all these configurations. So that was cool. It's a small little demo. And then what I did was I got 9 transformers, full size, 15 kVA transformers, and I'm going to make a little transformer wall. And we're going to say, okay, now you've got your delta, delta, delta Y, delta zigzag, delta, whatever Y, and then show the different grounding and bonding and connection, all this kind of stuff. But also, what we've done to make it safe is we've got all 480 to 122.08 volt transformers, but we're putting 48 volts in. So that means we get 12 or 20.8 volts out. So instead of 480 in, and
So let me ask you a question. When you're down that low, you have a 480 volt transformer and you're putting 48 volts.
It works. As long as you can magnetize it with
Well, that's not curious.
size of many transformers. We have a fairly decent sized 3 kVA transformer. So
Okay.
that we've got made that especially, and the other thing is too, it's not single phase, it's full 3-phase. So now we can look at things like the vectors and everything, which again goes back to that learning. Why did I learn about phasors and vectors? All this
Have you remember in class we used to do the saturation curves?
Yeah. I haven't done anything with around that space, but that would be interesting.
That would be interesting to do and to
explain it.
explain it. Yeah.
We talk about magnetizing current all the time. It would be good to show it more often. We do show some of the waveforms. We show the big peak and all that, and second, third, fourth harmonics and all that kind of stuff. 12 times inverse, 12 to 20 times. But that doing it with 48 volts and going to 120, 12 or to 20.8.
Yeah.
We really want to be able to show people with the scope, like here's your vectors, and like a delta zigzag. We were trying to explain it yesterday. That's a 0 degree phase shift. Well, what does that mean? Or split phase. How does that work? So we're doing single phase and 3-phase equivalents. That's going to be a cool demo.
So
it's going to be 9 transformers.
Oh, that's going to be nice. So I did this week. Well, now you know when we're recording this, because this is going to air in May and last week of May. But I did a video on the delta Y grounded transformer, and I was explaining the currents and the transposing your secondary to primary, right?
Yeah.
And using the equations. You got to go.
No.
Go ahead. So when I was doing that, when I first started, I said I think I called it transformer math or something like that.
Yeah.
And Don Gannier, God love him, he's like, talk about the 30 degree phase shift, right? And I'm like, I'm not going to do that right now. I'm just because it's going to be long enough just to talk about doing the math to get you from the secondary to primary and talking about when you have 3 single phase transformers and the delta and all those other good stuff. And then we did it Y to Y to explain why certain things work and from a math perspective. But it would be cool to if you could say, okay, let's connect this one in delta, this one in Y, and measure what's the voltage here, and then here, right? Line to neutral, line to line, and then do the math. So, okay, well, it's supposed to be square root of 3.
Yeah.
Right? And if you could show some of that, that would be awesome.
Yes. I think we can do that with that.
We could do a short circuit test too.
Yeah.
You could do a short circuit test to do the percent impedance.
Because we talk about that all the time.
Yeah.
With 3 single phase versus, so like the pole mounted transformers we've talked about, is it?
Oh, absolutely. Yeah. Because you have the center tap, right?
Yeah.
That pole transfer. Oh man, that's like an area I could even use some knowledge in that.
I think the big thing, Tom, is this really, this facility and the one we have in Houston, we can, even if we only used it for our own learning so that we could tell people how things work, it would be so much better. And the reason we've set these up is it's full scale. It's one thing to do a mock-up of stuff, but it is because it's full scale, we can do stuff like that and actually learn a lot ourselves and really reinforce what we may already know, or just look at it a different way, which to me, again, that's why I love doing this, because, I'm learning something every day.
Well, here's the thing. when you say reinforce what we already know, that's what you know. That may not be what I know.
No, exactly.
Right?
Yeah.
You know, so that's the other thing is I've been in so many classes where we talk, and I think it's a systemic issue.
Yeah.
Whenever I go to even if you go to some presentations, educational, and someone wants to talk about what they want to talk about, like transformers. I did a presentation in a location on transformers, and the way I laid it out, I used this tool called Mentimeter.
Okay.
And I said, we're going to work our way. The first step is we're going to work our way through selecting the primary and secondary overcurrent devices, primary and secondary conductors, okay, based on the NAC. The first step was to calculate full load amps, right? So what I did was I took an example of a transformer. I say it was a 75 kVA transformer or whatever. I said you have this much voltage on the primary, this much voltage on the secondary. You're going to calculate the secondary full load amps. And I says calculate the secondary full amps. And the answers were A, B, and C, and one of them was the right answer, right? So I said, okay, do the math, and then put your answers in. It's all anonymous. I had 80 people in the class, okay? 4 people calculated the fault current, the full load amps correctly.
Wow.
And I'm like, all right. So I said,
yeah,
if everybody except 4, I wouldn't go through, here's how you calculate full load amps.
Yeah.
Okay. So then I said, okay, we're going to go through, and I went through the slides because obviously we don't know how to calculate full load amps. So I went through the slides and said, I gave you the equations. All right, let's do a 300 kVA transformer. Put it up there. Boom. These are the 4 options. Do the math. 50% of the class did it right. I'm like, I'm still not.
You're getting better. How's that?
You're getting better, right?
Still, should have been 100%.
It should have been 100%, right? So then we did 8 transformers.
Wow.
It took 8 transformers, and then everybody in the class got it right.
Wow.
So I felt when I did the training, I felt like I didn't cover the material I wanted to cover. But I realized after the fact, I was like sort of bummed. And one of the gentlemen I was with, he said he was like, that was one of the best classes. And he goes, because he goes, everybody in that room understood. They learned something, and I verified it because he made a valid point. Once we calculated full load amps, then I was like, okay, well, we only got so much time left, right? This is a 2-hour class, right? So I'm like, okay, we have to pick what's the maximum size breaker on the primary, and they went 2.5 times, boom, like that, and they knew it. I said, what about the secondary? 1.75, boom, 1.25 times, boom, they had that, and I was like, okay, well, what would you typically put? 1.25 times. They went through everything else.
They have to have the basics.
But yeah.
And you wonder why they didn't have it, whether they never learned it or maybe they learned it wrong or something like that. Because honestly, like that square root of 3 thing will kill you every time. But the funny thing is, like, I think we've talked about this a couple of times too, is like you could learn something wrong and not know it's wrong, and then perpetuate that, make it even worse, because now you're starting to tell that story over and over. So now you, as whether it's an intentional or not teacher, teaching somebody else the wrong thing. And that calculation thing, we did one video that was over an hour long, and it has many, many views, over 100,000 views on it. But it's the same type of thing, calculating full load amps and fault curve for transformers, power factor correction, motor starting, all those things. I'll give you that link because that's
perfect.
That one is, again, you have to get the basics, and then you get. And that reminds me of another thing with power quality. Like when I used to go to conferences all the time on power quality, everybody wants to talk about the really sophisticated stuff. And I go, well, guys, you're talking about like 5 or 10% of all the problems out there.
Yep.
90% of the problems are down here. People don't understand this.
Exactly.
Don't bother going to there if they don't understand this. So you're exactly right on with that. That's good that you did that. I'm sure they all appreciated that.
Oh, I tell you what, I changed how I did a lot of my classes, but I tell you what, it's a lot more work, right? Because I mean, it took 8 transformers, and then you're like, okay, so I have to now figure out how do you turn your educational materials into Q&A?
Yeah.
Because I started that process of, all right, I'm going to ask a question. You're going to answer the question. If you get 95% of you or more get it right, I'm not going to cover the material. If you don't, then I'm going to cover the material. That's my deal. Right?
Good.
And I tell you what, it works out really good. But all right. So anyhow,
Yeah.
Man, we had a good conversation.
Yeah, that was fun.
And I appreciate you. I appreciate taking the time. I know you're busy. I see people walking around. They look. Yeah. So I'm sure they're like, we're halting progress. There's like 30,000 people outside just wanting to figure out what's going on.
It's all good. No, we do. We get about 8,000 people a year here, and then about the same down in Houston too. And it's
a lot.
It's really. I mean, we could do more if we literally had more people to host and do.
Yeah.
Because again, we insist on, because it's full scale and it's live. We turn the power on. We make sure it all is. But we have to have somebody here to bring people around. Otherwise, like, people are always like, "Oh, do a virtual reality or do a self-guided." I'm like, nope. It has to be done safely, and it has to be with somebody that's gonna. You've done stuff up here with people. You walk them through and you show, because you can be safe about it and you can show. But the point is, like, we have to show people what's real and how it works. I mean, otherwise they don't get the value.
Oh yeah, hands on. Now, which we'll close this session out with.
Yeah.
Let's talk about XL.
No,
EXL.
Yeah. So Experiential Learning. So, and that's the series that we have. So it's basically, we, for a number of years, probably 15 years or so, we've been doing what we call Power Up. And that's for the young consultants, new consultants. So 1 to 3 years out of college kind of thing, learning about that good, better, best. We've also been doing that with the apprentices and the electricians and contractors. So we have a program for them. We've also done it for utility engineers and people that work in the utility space. So we call that grid education. So grid education. And then we have the more advanced versions of these programs. So there's a variety of things. Like, we have a more advanced ones around data centers, and one on like next level stuff and even second and third level stuff on power distribution systems. So our application engineers typically help us, to teach some of the stuff, or we teach a lot of it, but we do it here. And then some of the classes are out in our satellite plants and stuff like that. So Chris Finnan, who's in charge of the AEs, he does a lot of the stuff, and his team does a lot of the training out there. But yeah, Eaton Experiential Learning. It's hard to say that.
I know. Experiential.
But it is a series. It's a number of things. Okay. It's not just one thing. And we're really excited about it.
There's a
website. Yeah. So I think it's Eaton.com EXL or something like that, but we'll make sure.
Yeah.
And then but the point is, like these people that were here today that we've kind of been working with, again, a very similar kind of crowd, and just, it's great to see their faces lit up. And you and I would have learned so much in this environment when we started. They say that all the time. And so what we're trying to do is just help people figure it out sooner than we had to do it. And the other thing is, there's not the mentorship that we have. We work with some of the most intelligent people in the world.
Yeah.
Oh, I know their backgrounds. And you go, well, I used to sit next to this person or that person or whatever. And, they literally wrote some of the Westinghouse books. And I learned so much from them. But when you sit there and you go, people don't have time, or they don't have the capacity. So yeah, it's important.
Yeah.
And I love what you're doing too. Thank you for all the stuff you're doing. And we get people in here all the time, and they're like, we show them the video of the race. So you should tie in the race maybe into this.
Oh yeah. We'll have to
sell the breaker contact fees. But they're like, do you know that guy? Like, tell him to Vitruvius. Yeah, I know him. It's like, he's awesome. He's free. He's famous. I know. Yeah, I'm sorry. He's a fuse. In the video, he's a fuse. He's a mess. I'm the breaker.
Fuse it or lose it. That's my
We've had fun. So thanks.
Yeah, we have. Thank you. And thanks for joining in on Shock Week. This is a whole series of videos, and you're going to be you're going to be getting phone calls. You're going to want autographs.
They're going to know, do you know Tom?
Yeah.
That's what they're going to ask you. You know Tom?
Did you know Tom has more hair than Dana? Wow.
It's true. He does.
Yeah, it's true.
Well, I'm a little.
Yeah, you are older than me. I look up to my elders. So, all right. So now, let's just thank you, sir. I appreciate your time.
Badly, go.
Check it out next week or whatever.